Take a look at number 15. So number 15 says to repeat the previous problem for the case in which the mirror is convex. Okay. So we're going to come in and we're going to take a look at a convex mirror. Okay. And so when we have the convex mirror, and that's this diverging mirror, which implies that our focal length will be negative. It also has other implications, like we're going to get a virtual image only. And so there's some things that go hand in hand with that. So with a convex mirror, then what we have is the diverging. Here. Okay. And so if we read ahead, then it says that there was an object is 0.600 centimeters tall, is placed 16.5 centimeters to the left of the vertex of a, in this case, a convex spherical mirror having a radius of curvature of 22 centimeters. Okay. So I guess I didn't put those down in on my list of formulas, but one of the things we have is that the focal length for a mirror is either plus or minus the radius of curvature divided by 2. And since in this case, since it's a diverging mirror, we're going to have the negative focal length. And so then we'll mark that one out. And so let me draw in a basic image. So we could picture that this is really a sphere. Well, we just draw the circle for the most part. And so then my center curvature is here. And then halfway from there will be the focal point. So center curvature, and then this will be our focal point. That is here. And they told me the radius of curvature is, I think, 22 centimeters. An object is 0.6 centimeters tall, 16.5 centimeters to the left of the vertex, radius of curvature is 22 centimeters. Now, one of the things we're going to find is that if everything is in centimeters, we can just leave our values in centimeters. We don't necessarily have to convert them all to meters, but we can. And so then we can calculate that this would be negative 22 divided by 2 is negative 11 centimeters for the focal length of our convex or diverging mirror. And it said that if this is 11, that we put it 16. So here's our object. We'll make it a little extra tall, so diagram is not really to scale. And it said that the object was 16.5 centimeters from the vertex. So that's our vertex. And it says that the object was 0.6 centimeters tall. So this is our object height. This is going to be the object distance. Since the object is right side up, then it's going to be a positive object height. Since the object is in front of the mirror, this is a positive object distance. And since this is a diverging mirror, we need the negative focal length, which is just half the radius of curvature. Okay. And so there's my image. And then it says, draw a principal ray diagram showing the formation of the image and then calculate position, size, orientation, and nature of this image. So let's go ahead and do our ray diagram first, and then we'll run the calculation second. And so then the first ray is going to go in parallel to the principal axis. So. And then it will reflect off the mirror as if the ray came from the focal point. Okay, so there's ray 1. Now, the second ray, you're going to go in through the focal and will come out parallel. Well, we're never going to make it to the focal, but we're going to shoot as if we would go to that point. And so the ray heading like this will go through the focal, and once you hit the mirror itself, then what happens is it's going to reflect. And it's going to come off parallel to the principal axis. And then our third ray is going to go through the vertex. And so then I'll take my object, flip it upside down, mark the dot, go from the tip to the vertex and draw in our ray. And then draw from the vertex to the point where I inverted it. Other ray. And what we notice is that the outgoing rays, this one, that one, and this one, diverge. So then what we'll need is a viewing eye to trace the outgoing rays backwards. I guess I didn't use blue yet, so we'll do blue. And so if we trace our outgoing rays backwards, this outgoing ray backwards, this outgoing ray backwards, this, then it appears as if the image is right here. Now we can talk about the characteristics of our image just from the diagram, okay? And so the first thing is, well, is it real or virtual? And we would get what? It is virtual because we had to trace it back. Then this is the virtual. And then we can look at whether the image is upright or inverted. And since there's only one lens or mirror, then all the virtual images will always be upright. And since this was a diverging mirror, which only produces upright virtual images, they're also always reduced. So if you have an enlarged upright virtual image, then that was with a converging mirror or lens. The diverging ones always produce these reduced virtual images that are always upright. And again, if you have more than one lens or mirror, all of those little associations go, out the window. So, so there we go. So this is the stuff that we know. So let's go in and let's calculate some things. Okay. We know that it is a virtual, upright, and reduced image. And technically we knew all of that once we knew it was diverging. But I like to draw the diagrams and just see the things come out, because for me, that's easier than just kind of remembering that, oh, it's always this way. But it is always this way. Okay, as long as you have only one lens or mirror, and that's the thing. So we have our object distance and we have the focal length, so we can calculate our image distance, which is this distance here from the vertex to the image. And so we would do that 1 over the focal is 1 over the object distance plus 1 over the image distance. And so then this will give us 1 over negative 11 centimeters is 1 over positive 16.5 centimeters plus 1 over I don't know. And so then we will move this to the other side. And then I'm going to go in and flip the equation because I'm annoying like that. So then this is going to be minus 1 over 11 minus 1 over 16.5. And then with this, we can go in and solve for our S prime. And so we can do that little, similar to the series capacitors and parallel resistor little trick with the, the invert, the reciprocal buttons on the calculator or the series of buttons. So we can see it's definitely going to be a negative. And then it would be like our resistors and capacitors, where it'll be smaller than the smallest one, but not smaller than the smallest one divided by how many. So we're kind of looking less than 11. It'll be negative, but less than 11, between 11 and half of 11. So what, 5, 5, negative 6, 6. There it is. Since everything's in centimeters, it comes out in centimeters. And so there we go. Okay. And now that we have the image distance, we can go in and we can calculate the lateral magnification. So the magnification, essentially by definition, is our image height over the object height, but we can also get it as minus the image distance over the object distance. And so that's one we're going to go with. So this is minus the negative 6.60 centimeters over our object distance, which was plus 16.5 centimeters. And so then the minus gives us a plus. And then we see it 6.6 over 16.5. And so since this factor is number one positive, that means my image is upright. Upright over image over the height over the object height. So if it's positive, they both go the same way. And it's going to be less than 1 because we reduced it. So this is a 0 point smaller than half, right? Because a half would be 8.25, but 6.6 is bigger, but it's less than that. So 0.4. And then notice that this is centimeters over centimeters, and so those just cancel. So magnifications don't have any units. Now, personally, I'm very used to seeing that I would put in a little time symbol like this, but I think our book is anti-time symbol. Okay, so I think they don't write this at all. They'll just write the 0.4. But I like the 0.4 times because you see that on the eyepieces on like the microscopes and on the telescopes and things like that, is you see this times imagery. So I kind of like to include that. And so then once we have the magnification, we can get the image height just by, multiplying the object height over like this. So then this is our image height is the magnification times the object height. So we take our plus 0.4 and we multiply by this plus 0.600 centimeters. And 4 and 6 is what, 24. So this is plus 0.240 centimeters. So there's our image height. And so at this stage, we pretty much have everything. We've got the image distance, magnification, image height. And so there we go.